Standard LLM APIs handle isolated chat queries with high efficiency. But when these same models are tasked with complex, multi-step enterprise workloads, the architecture shatters. These systems fail at specific, predictable points. External API timeouts kill the process. Models execute hallucinated tool calls with no verification, and the context window inevitably drifts, causing the agent to lose sight of the original objective. Solving this requires a shift in engineering logic. We must move past writing linear prompt scripts and begin engineering fault-tolerant state machines. A production-grade agent task orchestration system requires a dedicated blueprint. This blueprint relies on 5 mandatory engineering layers: memory and decomposition, modularity, pipeline efficiency, state management, and system resilience. Without this framework, LLM implementations remain unpredictable scripts. With it, they function as resilient, scalable enterprise systems. Intelligent task decomposition must occur before a single tool is invoked. Large, complex goals have to be broken down into manageable segments. We evaluate 2 reasoning patterns. React uses a continuous loop of reasoning and acting. It uses fewer tokens, providing faster responses for simple dialogues. Plan and execute separates these phases. It costs more, 9 to 14 cents, but reaches 92% accuracy on complex tasks. That accuracy comes from the planning phase, which analyzes task objectives and resolves dependencies to ensure no compute time is wasted on dead-end execution paths. During the execution phase, the agent processes these subtasks in order, validating intermediate results before moving to the next checkpoint. Running these extended reasoning chains depends on a hierarchical memory system. The agent needs specific retrieval and indexing to maintain context across long-running tasks. Choosing reasoning patterns allows engineers to control the system's primary levers: latency, cost, and task accuracy. Hard-coding specific tools into individual agents creates immediate technical debt. As the system grows, managing those direct connections becomes impossible. We solve this by implementing a tool management platform, which serves as a centralized, dynamic registry for all enterprise tools. When an agent identifies a need, it requests a capability from the registry. The platform then provisions the authenticated, standardized interface required for that tool. This centralized layer enforces strict access control and monitors the health of every tool endpoint. If an API goes down, the registry knows immediately. Decoupling these components allow engineers to update, swap, or deprecate individual tools without ever modifying the core agent logic. This abstraction transforms an agent from a fragile script into an extensible, secure platform. To prevent bloat, we use 2 parallel pipelines. Synchronous pipelines handle simple, instant calculations. For intensive tasks like file analysis, we use the asynchronous pipeline. The agent drops the task into a pool, receives a tracking ID, and continues its reasoning chain without waiting. This parallel architecture allows background workers to process heavy data loads while the agent maintains its core reasoning thread. We optimize hardware use through dynamic resource allocation, setting specific usage limits for these background tasks. Task batching further increases efficiency by grouping similar asynchronous requests to reduce redundant compute overhead. We also employ multi-level caching. By intercepting redundant API calls at the cache layer, we significantly lower total token expenditure. Pipeline bifurcation ensures that analytical bottlenecks never block the agent's ability to observe and react. Coordinating these decentralized components requires an orchestration framework. In production, we use LangGraph. LangGraph treats workflows as rigid checkpoints. We define specific states for the task and use defined transition logic to move data. If a tool fails mid-execution, state persistence saves the progress. Instead of losing the task, the system locks the current state in place. APIs will crash, and agents will occasionally hallucinate parameters. A production system must be built to handle these failures gracefully. We build resilience through retry mechanisms and strict parameter validation. To prevent infinite loops, we deploy forced timeouts and exit conditions. If a path is unrecoverable, the system triggers a state rollback, reverting to the last safe checkpoint, so corrupted data never reaches the output. Ultimately, state persistence transforms these non-deterministic LLM failures from catastrophic crashes into manageable, fully recoverable system errors within the architecture. A production-grade agent functions as a vast, interconnected orchestration layer that wraps the underlying foundation model. When a complex market research prompt arrives, the plan and execute pattern immediately breaks it into an organized tree of subtasks. These subtasks move through the registry, where the system assigns validated tool endpoints to each discrete requirement. Execution flows through parallel pipelines, using the async pool for heavy analysis, while LangGraph saves the system state at every checkpoint. The intermediate results are merged, verified, and returned as a single output node, with no loss of context. Enterprise-grade AI requires applying rigorous distributed systems principles to LLM non-determinism. By combining modular tools, async efficiency, and state machines, we turn fragile AI potential into robust production reality.